And once you are ready, we can start. We are already 17, so I guess most of us are already here.
All right. So it's a pleasure to talk to you all about some kind of hybrid overview slash new research talk um, about bosonic error correction. And I guess I first want to start with a review of what is the purpose of error correction, classical or quantum. The purpose is to preserve messages sent through a noisy transmission channel by encoding the messages in what's called an error correcting code. So you have some message row, and I want to again reiterate, this can be classical or quantum. This kind of framework was started over 7 years ago by Shannon, and it applies equally well to both scenarios. You map this message into a larger space so that you can utilize the redundancy of the larger space to store it in a way that's robust against noise. You do that using what's called an encoder. Then you send your message through a transmission channel. Now, this could be a communication channel, but it could also represent a hard drive that stores information in fixed space, but in time. And at the other end, the receiver, which could be you at a later time or somebody else in a different point in space, is supposed to extract this information. They do this using a decoding map or a decoder. And the point of error correction is that this whole entire sort of more complex process than just sending the message straightforwardly will get you back the message more or less intact. This type of framework has been used and is continuing to be used as we speak on our Zoom meeting and cellular communication, space communication. But of course, with the advent of quantum correction, we're all probably here to kind of discuss more the quantum side of the story. And that's what I guess I'm going to do today. And feel free to ask questions. It's always hard to give these online talks because it's hard to gauge audience reaction. So the particular type of error correction I'm going to talk about is the use of error correction in continuous variable or bosonic systems. And these are specific type of quantum system where the position and momentum or the conjugate variables are characterized or are continuous degrees of freedom. These could literally be the position momentum of a mechanical oscillator or the quadrature components of an electromagnetic field mode. I think many of you are experts here in this, but I'll still motivate it. There's lots of actually different types of platforms that are modeled by continuous variable spaces. And so the reason we need to study these for the purposes of robust communication and storage is because we will have to be using them at the very least for the communication. There's no better way to communicate than through optical fibers and free space communication, and these are indeed continuous variable systems. Moreover, systems that are trying to scale up for quantum computing, some of them do have extra levels that, when taken together, form a kind of oscillator, a continuous variable system. Those extra levels are not being utilized because it's kind of a problem to control them in some instances, but it's actually not as bad as it used to be, and one could imagine trying to utilize those extra spaces for storage and for different protocols. So there is extra space at play already in current systems, such as Rydberg atoms, that could be utilized for this type of analysis. Often these types of systems, in the case of microwave cavities, were built with naturally long lifetimes. And so it would be interesting to see, I mean, it's natural to try to encode information in them because they are indeed seem to be kind of born to do it. And of course, it's just kind of fun to do this math. And so this is what this talk will be about. Another motivation slide, the fact that the position momentum are continuous means that the space of the state space of this system, which is spanned by many different things, but let's say Fock states, a countable infinite basis, is infinite dimensional. Now, this means that there are many theorems that were formulated for finite dimensions that do not apply. And I'll just be kind of listing these. So for example, there's no, you can have continuous parameter families of transversal gates in infinite dimensions. You can have a C-naught gate, a logical C-naught gate that's continuously connected to the identity in infinite dimensions. And this allows you to have some what's called bias preservation, some fault-tolerant properties. And if you utilize the kind of the infinite dimensional space or a subspace of it, you can, by some metric, use fewer resources or require less overhead than if you were to consider codes out of qubits or protocols out of qubits. So you'll see some of this through the talk, but I just want to flash this slide in. Right. So to me, error correction is, as I'm hoping to get across, very general. And to me, it kind of starts off with picking what you're going to be using for your encoder. And in classical information theory, the set of symbols you use for storing your information is called an alphabet. You're familiar with bits as the primary alphabet of choice for everybody, but in classical coding theory, people are also obsessed with finite fields, something we don't see a lot in quantum. And those are these FQ symbols. In quantum, we more are interested in codes over rings, which is just ZQ. But these are basically two types of qubits that you can have when you generalize bits. And you can likewise use the reals for the alphabet, which was actually the original alphabet used by Shannon, and the alphabet used in transmission of information using electromagnetic symbols or electromagnetic fields. And you can generalize these to finite groups as well. So this is something that people study in classical. And then if you want to transition to quantum, there's a very simple picture to do this. The point is that quantum code words are wave functions or functions on the alphabet that you use for the underlying classical code. So if you take functions over bits, you literally have a wave function. And so you can define a qubit. And similarly, you can define qubits for both fields and rings. And if you do this mapping for the reals, you just get the oscillator, harmonic oscillator, continuous variable system. And likewise, there's a kind of sparse set of applications for the more general group-valued qubit systems that I won't discuss, but you feel free to ask me about them a little bit. I can discuss. So this is, to me, kind of like the side-by-side comparison of error correction for classical and quantum systems. And using this kind of universal sort of comparison, you can also construct, in a very simple fashion, error-correcting codes. So in classical coding theory, error correction is basically a packing problem. Your noise is only one type, bit flip. And the point is to develop or create a set of pick a subset of your elements of your alphabet such that they're spaced enough apart so that bit flips don't map them into each other. So for example, if you have 3 bits, you can pick the repetition code where you're encoding 1 bit into 3, and you want to do that so that you're protected against as many bit flips as possible. And so you place them as far apart as possible in the metric that's defined by the amount of bit flips that you need to get from one to the other. And here you can draw a cube labeling all the 8 elements of the alphabet, and you just place your code words at opposite corners of the cube. If you want to say store more information, you have to kind of pepper in these code words in a well-separated and uniform fashion so that you can get as many of them in there and have them still be separated. And so if you have, say, 4 bits that you can use, you can create this particular classical code, this single parity check 432 code, encoding 3 bits into 4 and protecting against 1 bit flip. And that's basically classical coding theory. I mean, it gets very complicated because they use lots of fancy math to do this, but you're effectively kind of peppering in code words such that they're separated and more or less uniform. Now, and you can do this for these other alphabets that I mentioned as well, like lattices. So lattices are codes in R, where again, it's the same kind of intuition. You have some set of uniform, well-separated points. And likewise, this is something that people have been doing for a long time. You can place points on a sphere. So a sphere in classical coding theory represents the space of signals of fixed energy, just like the real space represents the space of signals. This goes back to Shannon. So armed with this type of construction, there's a very easy way to map all these to quantum. It's not the only way, it's just it's a primitive way to do it, but it does give you quantum codes right off the bat. Namely, in quantum space, you have to take care of a separate type of noise in addition to bit flip called phase flip noise. And this is because you're storing quantum information, which is stored in superpositions of the elements of your alphabet, logical 0 and logical 1, for example, for the case of a qubit. And these superpositions can be corrupted by changing the relative phase between the two elements in the superposition. This type of phase noise doesn't affect your classical codes because there are no superpositions in classical coding theory. You're just sending one of those white balls at a time through the channel. But now in quantum, you have to take care of this. And the way you take care of this is you just take your classical code, split it up into two or more subsets, and superpose the elements of each subset to get you protection against phase noise. So in the quantum repetition code, you can't superpose anything. You just split the two balls into a red or a black and a white ball, and you use them for the two logical states. And there's no correction against phase flip noise here. However, if you take, say, your 432 single parity check code, you split the balls into sets of 4, and you superpose each of the 4 pairs of different colored balls and make your basis for your logical code words. You get the 422 code, which encodes 2 logical qubits, basically 4 states, into 4 logical qubits and detects 1 single qubit error. So the reason this code protects against phase flips is because your code words are themselves superpositions of basis states. And so if your relative phase is changed between the logical states, there is a way to detect and correct the error. The kind of underlying maybe deep message here is that quantum error correction requires entanglement. The fact that I have to write each code word, each of the 4 basis states as a superposition of 2 canonical basis states, like the white balls are, say, all 0 and all 1, all 0 plus all 1, tells you that you actually need this, tells you that each of those basis states is entangled, and you actually need that entanglement in order to have a quantum error correcting code. So we've played this game for the top 2 Hamming cubes. We can do this for the lattice as well. If we split our lattice in kind of a checkerboard tiling, and superpose all of the black balls to get a logical 0 state and all of the white balls to get a logical 1 state, we get what's called a Gottesman-Kitaev-Preskill code, or just a quantum lattice code. And this code has protection against both bit and phase flips, which are in this case shifts in position and momentum respectively. And likewise, we can do this with spheres. We can take our points on a sphere, split them up into 2 sets, and superpose them to get what's called a quantum spherical code, which is one of the things I was going to talk to you about today. So, right, so if anybody has any questions, definitely feel free to chime in or ask. This is a very primitive kind of basic kind of CSS type construction that allows you to get quantum codes out of basically any kind of space in classical world.
So in GKP, you only encode 1 qubit. In the sphere, also 1 qubit in what you have shown us here. I'm not
the pictures I've shown you here, yes, but you can play that. It depends on how much you split, how many subsets you split your points into.
Okay. Thank you.
Thanks. So the quantum spherical codes I'll be focusing on for the next few slides, because that's kind of one of our kind of interesting things we were working on last year. In the way I showed you before, they're basically analogs of classical spherical codes. So a spherical code classically is just a set of points on a sphere. And so the construction I showed in the previous slide can be used to create quantum spherical codes. And the interesting part is this kind of construction allows you to create codes in any configuration space that contains a sphere. So the primary configuration space that you may be thinking about is the one spanned by coherent states of fixed alpha. And that's the one we'll be talking about in the talk. But I want to mention that there are other ways to construct spherical configuration spaces using all sorts of these other coherent states that you're probably familiar with. In addition, you can also play this game in the space of orientations of diatomic molecules, because their position states, their orientations, are also points on the two-sphere. There's two types of noise on the sphere. One is just literally isometrically moving on the sphere, using rotations on the sphere. And that kind of bit flip noise. Protection against it is characterized by the minimum distance, the minimum separation between 2 points used to construct your code. So this you inherit from the spherical code when you treat it classically. But then phase flips correspond to the environment inducing some potential on your sphere that takes different values at different points. And if the environment can use that potential to sense whether you're in the logical 0 or logical 1 state, then the environment will be able to extract your information and ruin your error correction protocol. So phase flip noise you can think of as potential functions on the sphere, and you have to check whether potential functions up to some certain order are protected or detectable or correctable. You can expand these potential functions in some expansion of using polynomials, and in the case of coherent states would be using loss and gain monomials, but you can also use other bases, for example, spherical harmonics for the molecular codes. So this is what we'll be talking about now. Maybe not for this audience, but I do want to review, at least briefly, what a coherent state is. It's kind of just a Gaussian blob in the phase space of a harmonic oscillator. It has to be a kind of a blob and not a point because of Heisenberg uncertainty. And you can think of it, you can do it for one mode, but you can also do it for n modes, which is what we'll be doing, because then you get higher dimensional spheres that make things way more fun. And there's an analog here between 1 and n modes. Basically, the Hilbert space distance is proportional to the exponential of the Euclidean distance between the actual points labeling the coherent states. So they're almost orthogonal, but not quite. The type of, as I was saying, phase noise and z-type operators are potential functions on the sphere, and those are obtained by applying lowering and raising operators and projecting them into this coherent state space using this famous equation that coherent states are right eigenstates of the lowering operator. So those are not going to be unitary, but they will be still useful to quantify phase noise. X-type operators are going to be your uniform rotations, as I mentioned. And in what single mode case, there's only one rotation, but in the multimode case, you can have these Gaussian beam splitters and phase shifters that will implement a unitary transformation on your sphere. And if we're going to be fixing states to lie on a sphere, so we have to have all our alphas, all their norm has to be fixed. And we can fix them to some reference number, which we'll pick to be 1. And then we can scale the sphere as we see fit by an overall scaling factor later on, which will just be the total energy that we put into the code. Okay. So the thing that I thought it would be most fun to do once we've noticed this connection was to use polytopes to construct quantum spherical codes. So this yields an extension, a natural extension of these cat code type of error correcting codes, which correspond to polytopes in 2 dimensions, such as triangles and squares. So here, you remember the white and black balls. I have each set of balls used to construct a code word forms the vertices of a triangle or the vertices of a line segment. And those are superposed to form a code word for the cat code. So the fun thing to try to do is to try to extend this to higher dimension using multiple modes. So now here you have in 3 dimensions 2 tetrahedra that you can, each of whose vertices you can superpose to form a code word of a quantum spherical code. Similarly, you can pack 5 tetrahedra and make the vertices of a dodecahedron, and so you have a 5 logical dimension code that you can superpose to get a nice, and you still have a nice polytope. And with, you know, larger numbers of modes, we gain access to higher dimensional spheres and therefore higher dimensional polytopes, which you can't really visualize in 2 dimensions. So I'll go through some of these codes, and I'll set up the framework using the famous cat code. So cat code is a simple, like one-dimensional set of points on a circle. The simplest one is kind of like the analog of the repetition code. It puts points on antipodal points, uses antipodal points for the code words. And there's basically you can think of a stabilizer for them as being a squared, because a squared doesn't tell the difference between alpha and minus alpha because it's a squared. And you can use this kind of fake stabilizer to create a continuous double well type potential for this system that's quantum, namely that it can preserve coherences between the 2 wells and stabilize them in the lab this way. So this monomial a squared acts as a z-type stabilizer because it evaluates to alpha squared, as I was saying. Likewise, if you take the square root of it, use the a operator acts as a z-logical because it sniffs out the sign of which code word you're in. If we now think about x rotations and x-type stabilizers, the Gaussian rotation that exchanges the 2 will act as an x-logical. So that can be used as a gate. Right, so that's kind of the framework. And you can extend this to multiple components. So now each set of balls that I'm going to use, I'm going to call a constellation. And in this 4-component cat code, which is the simplest generalization, I'm going to use alpha and minus alpha for the first constellation, C0, and I alpha and minus I alpha for the second constellation, C1. So here alpha can be fixed to be 1, or it can just be thought of as an overall scaling factor, or overall real scaling factor model, like signifying the radius of your sphere. The 2 constellations form the vertices of these 2 line segments. So now we have, as before, we have some protection against rotations, and that's quantified by the minimum distance between the points, which I'll call the resolution, and I'll use this minimum Euclidean distance. So in this case, it's square root of 2. In the case that alpha is 1, these code words are superpositions of different coherent states. So there is some protection against loss and gains. Namely, there's ability to detect and correct 1 loss or 1 gain. And these 2 distances, the amount of losses and gains and the resolution, give you kind of a trade-off. So the more points you use to pick to in your constellation, say triangle, square, pentagon, the lower your resolution will be because you're trying to squeeze in more points on the circle. So you're going to be protected against less rotation errors. However, you're going to gain more and more protection against losses. And so there's a trade-off that you can use here. This kind of is a very general feature that happens in error correction, that you have these 2 types of noise and you can't protect against both perfectly. And you have to pick which one you want to protect against more, which one you want to protect against less. In terms of stabilizers, in this case, a to the 4th acts as a z-type stabilizer, evaluating to alpha to the 4th, and a squared is a logical because, again, it sniffs out the sign of both of the code words. Here we have a logical, you can see the geometry if you just exchange the 2 line segments by rotating by 90 degrees, that acts as a logical gate. And in this case, you have actually a stabilizer as well, because if you rotate by 180 degrees, your segments are left invariant. Okay, so what's new now? So let's go to multiple modes. So we're going to go to 2 modes now and introduce kind of the simplest quantum spherical code. Now we're going to have encode a logical qubit, and the constellations we're going to use will form the vertices of a simplex in 4 dimensions. So it's kind of like a generalized tetrahedron. It's called a 5-cell. So these kind of simplices are exist in each dimension, and they're just sets of points such that the distance between any 2 points is the same. So equilateral triangle, tetrahedron, and then there's this thing in the next dimension. The reason we have 4 dimensions is because we have 2 modes. Each one is complex, so we have 2 complex dimensions or 4 real ones. And the constellation points are going to be these 5 points, and they're going to be just powers of 5th root of unity, but there's a 2, notice, in the second mode, so the power of the second mode iterates faster than the first. And that's the logical 0. The logical 1 will just be the inversion of that if you flip every point in the constellation to minus itself. So what's cool about this code? Well, not too much. Its resolution is lower than that of the 4-component cat. However, it is able to detect 2 losses as opposed to just 1, but it only corrects 1 loss. Again, you have kind of stabilizers for it. You have these monomials that act as Z-type stabilizers. They don't tell the difference between the 2 code words, and you can kind of stare at it and evaluate the constellation points in these monomials, and you'll see that they evaluate to the same thing. AB squared will act as a Z-logical, so it'll spit out the sign when applied to each of the 5 points in each code word. In terms of rotations, now you have 2-mode rotations you can use, and the joint parity acts as an X-logical, because if you flip the sign of both words, you have C0 going to C1. And a stabilizer is the 5th root of unity, is kind of this generalized Z5 kind of rotation, generalized parity, acts as an X-type stabilizer. So as I was saying, simplices exist in any dimension, and so you have this kind of first infinite family of quantum spherical codes. They get better in resolution, so their resolution is, I think, 2 minus 2 over root n. So as n goes to infinity, then it approaches 2, the resolution. And that is the same as the resolution of the 4-cat code. And there's an extra benefit in detecting 1 more loss. But other than that, this family is not that interesting.
So one question is to consolidate ideas. In the previous one, in the cat code, you basically have 2 states associated to 0 and 2 states associated to 1. For instance, 0 would be alpha plus minus alpha. If you lose 1 photon, alpha plus minus alpha transforms into alpha minus minus alpha, and you can detect that experimentally. But if you lose 2 photons, you go back to the original state, so you don't detect those events. Here, you have 3 states before you return back to the original one. So did I understand it correctly? So the fact that you can detect 2 losses is that you have, this is periodic under 3 losses, or something like that.
Yeah, I think you have the right intuition. I don't remember the specific periodicity, but there is a periodicity here.
Okay.
Is the point. You don't always have periodicity, and I'll show you codes where you don't have it, and you'll see why. But here, yes, there is a Z5 type periodicity because everything is a root of unity to the 5th. There's a 5th root of unity.
Okay.
So you have, if I can remember. So there's a code space and 4 error spaces, I want to say. And to correct 2 losses, you need like 1 more error space, but you have 2 errors colliding on 1 error space.
Okay.
And I think if you just let the losses happen, there is a cycling through between these error spaces with some periodicity.
Okay.
Yeah. And so that's another interesting thing about this code, that the constellations are arranged in a very nice way that you basically can just kind of track and not have to correct. As long as you track fast enough this Z5 syndrome, you can just have the information cycle between the error spaces and the code space.
That's clear. Thank you.
So this is a code where you don't have that happen, because now it's a 3-mode code, but the points are arranged such that one of the coordinates is 0. And so now you lose this periodicity because as soon as you have a mode loss, a loss of a photon in that mode, the whole coherent state is annihilated. And so you don't have periodicity anymore. In this case, it's not clear whether you are able to maybe rotate this whole polytope in some way to get back the periodicity. That's an open question, but in this specific manifestation of it, you don't have that. So, but nevertheless, this is a very interesting cat code. So this code uses the Hessian polytope. It requires 3 modes. And here are the constellations. Now, eta is a third root of unity. And again, you have a qubit because I'm using a Hessian per code word, and I'm just inverting one into the other for the qubit states. The resolution here is 1, the same as that of the 6-component cat. However, it detects 8 losses, which is as powerful as the 18-component cat, and it corrects 3 losses, which is as powerful as the 8-component cat. So using extra dimensions to pack your sphere points on a sphere more effectively allows you to sort of outperform the cat codes in terms of code parameters. And again, there's the same kind of story with these stabilizers. This particular Hessian code is related to some stuff from algebraic geometry, and so there's kind of beautiful looking stabilizers for it that are very symmetric. And I have a typo. The third one requires you to, the third one fixes the radius. So the third one should be a to the 6 plus b to the 6 plus c to the 6 plus alpha squared, which is this real number scaling the radius. But the first two don't actually require alpha, which is interesting because you can see that, ABC, for example, will annihilate all of the coherent states involved because it'll always be 1, 0. So you don't need an alpha for the first two. If you want to think of gates, you can use only lowering operators. You have to have something that's kind of order 9, a third, b6. Or if you allow for raising operators using this kind of like, by projecting them into the code space, you'll see that a dagger ab cubed also acts as a z logical. Another interesting feature of this code is that it's more quantum than the cat codes in the following way. If you look at the total degree of the stabilizers, the sum of the powers, you will see that some of the stabilizers, the degree is less than that of the logicals. So the logical degree, if you use only lowering operators, is 9, but there's stabilizers that are degree 3, the first two, and in fact degree 6. Now, what does this remind you of? Well, it should remind you of the surface code, where you have logical gates that are, that have to be strings going around a torus. So they're basically the size of the lattice, the length of the lattice. And stabilizers, they're just weight 4. And this is the same kind of feature. Your stabilizers are lower weight, lower degree than your logicals. And this did not happen in the cat code, because in the cat code, it was the opposite. You had to take the square root of the stabilizer to get back. Sorry, you had to take the square root of a stabilizer to get to a logical. It was a lower degree, but in this case, it's higher. Okay, so if you do, now if you consider rotations, you have 3-mode rotations. Again, because I picked a qubit, it's very easy to get the X logical. The X stabilizer group now becomes more complicated, because now your stabilizer, your set of X-type stabilizers consists of Gaussian rotations that correspond to cyclic permutations of the 3 modes, as well as things that shift your phase by root of unity for the 3 modes. So let's look at that a little bit more detail. How do you get the gate group? And what kinds of gate and stabilizer groups do you have for quantum spherical codes? Well, it all has to do with polytopes. The data that you were using to construct these particular quantum spherical codes are polytopes. So we have to think about what the polytope is and what its symmetry group is. So we have 2 different types of polytopes. We have to use a polytope for each of the code words. And then those are let's call the code word polytope. And then together, the union of all those vertices form another polytope. You can call it a polytope compound, or a logical polytope, or sorry, a code polytope. Now, each code word polytope has a symmetry group. If we use the same code word polytope, just rotated versions of it, then the symmetry group H mu of each polytope, code word polytope mu, will be related via rotation to the symmetry group of the other polytope. And then together, the code polytope will have a bigger symmetry group, and all of the code word polytope symmetry groups will be subgroups of it, different embeddings of the same subgroup inside the big symmetry group G. Now for cat codes, everything's abelian, meaning commutative, so things are very simple. Both code word polytope groups H0 and H1 are just Z3, and G is Z6. And H0 is equal to H1 because it's the same group. It doesn't have to be the case in general because the things don't commute. And so a subgroup H embedded into G this way is different than a subgroup H embedded into G another way. So this makes things more complicated and kind of interesting. Because now if you use this data, these symmetry groups, to construct the stabilizer group, you have the following thing. The stabilizer group has to leave each code word invariant. Okay, it can permute the points in the code word polytope, but it can't map a code word polytope to another one because that would be a logical gate. So it has to leave each code word polytope invariant. And the only operations that do that lie in the intersection of all of the code word polytope symmetry groups. In the case of the cat code, again, everything is abelian, so it's just Z3, the whole thing. But when the groups are different manifestations of some subgroup or of some group H, then you have to take their intersection. That's called the core. And this group, this resulting group, the stabilizer group, can vary in size quite a bit. So I was going to show you one example by that, of two examples where the group is very small or very large. So once you define the stabilizer group, you just then take the rest of the elements, and those will be your logical group. And you can bin them into classes of different types of logical operations to get this group L. So let's pick one example. Let's go back to our Hessian. So this is an example of where you have a large stabilizer and you have a small, as a result, very few of your elements actually do any logical operations. The polytope symmetry group of the double Hessian polytope is this group, some Coxeter notation for the polytope symmetry group. It's got 1,296 elements. Okay. How many of them leave each of the two Hessian polytopes invariant? Well, turns out half of them do, 648. And there's nothing left except Z2 for your logical state. So the only thing you can do is exchange the polytope, kind of like in the cat code in the upper right. So the stabilizer group is huge. The logical group is just Z2. Using Gaussian operations, the best you can do is just a logical X. And let's think of the opposite now. This is a code that finally doesn't encode a qubit. It encodes 5-dimensional qubit. And it's a 4-dimensional generalization of this 5-tetrahedron and a dodecahedron code I showed you in the beginning. In this case, you have 5 24 cells, which are these polytopes in 4 dimensions. And you can rotate them around, and that way you can tile this big 600 cell. And each 24 cell has 20 vertices, and the 600 cell will have 120 vertices. Okay, so the symmetry group of the 600 cell is the kind of like a generalized icosahedral group. The 600 cell is kind of like an icosahedron, but in 4 dimensions. It's got 120 elements. In the way I've embedded this in 2 modes. I'm going to say that. How many of those elements leave the code words invariant? Only 2. Just the inversion, kind of like an inversion piece. And the rest will always permute the 24 cells amongst themselves. And that gives you, when you mod out Z2 by 2i by Z2, that gives you the icosahedral group. So the logical group is a permutation representation of the 60 elements of the icosahedral group that just permute the 5 different 24 cells amongst themselves. So using Gaussian rotations, you can implement a very large group that you can't do with less than 7 qubits if you were to do this in a qubit code. But here you can do it already with 2 modes at the expense of losing sort of almost all of your stabilizers. This code is powerful. It can protect against many losses, but it only has one error syndrome if you were to use Gaussian operations to detect and correct it. So I think there feels like there's a general, again, a gate stabilizer trade-off if you use some set of canonical operations here, like Gaussian operations, for your gates and your stabilizers. You can only use them in one or the other way. So those were the polytope cat codes. There's another sort of class of quantum spherical codes that we sort of found. We didn't really find them. We just kind of interpret existing codes as quantum spherical codes. And these existing codes are just concatenations of cat codes with so-called qubit CSS codes. And CSS codes are just some set of multiple qubit codes that have a notion of an X-type and a Z-type distance. And if you take you can map a CSS code, or you can concatenate it into with coherent states just by mapping the 0 and the 1 in each basis state into alpha and minus alpha. Okay. In classical physics, it's called the antipodal mapping. And this is something that people have been doing for the past 7 years, studying various concatenations of, say, a surface code where now each of your physical qubits corresponds to a cat code in alpha and minus alpha. But we're going to look at it in the bosonic direction now. What previous works have been doing was looking at the qubit sort of side of the story. We're looking at the bosonic side now. And in the bosonic side, it's actually another type of spherical code. And both of the distances that the spherical code has are inherited directly from the distances of the CSS code. So the CSS code has a Z distance, phase noise distance. That actually automatically tells you that loss and gain monomials acting on the modes are detectable on at most dz-1 modes. Similarly, CSS code has a bit flip distance. In Hamming space, dx is the number of bit flips you need to map one CSS code state into the other. Okay, but we're in coherent state land on a sphere. Well, it turns out the Hamming distance between the binary strings is mapped naturally into the Euclidean distance between the coherent states, the antipodal coherent states on the sphere. And so this dx CSS distance gives you a resolution or a minimum distance between coherent states of your concatenated code that's 4dx over n. You can play this mapping with stabilizers as well. Z-type CSS stabilizers become your stabilizing Lindbladians. So basically, anytime you see a Z in your CSS code, map it to an A. Okay. And this gives you actually a new way to protect against dephasing noise that hadn't been appreciated before, using, say, surface code stabilizers, which are, ZZZZ. They act on some star or plaquette. Or sorry, let's fix them to act on a plaquette. And you can imagine cooking up a Lindbladian degree 4, A1, A2, A3, A4, that protects you against dephasing in the same way, in a kind of an analog way that the stabilizer protects the CSS code against dephasing. Of course, because you're mapping each physical qubit into a coherent state cat code, you need to additionally stabilize the individual alpha minus alpha cat code states on each qubit. So you're requiring these additional stabilizers. This is something people have, of course, done. And similarly, you can do gates. Anytime you see a Z, you map it to an A. And so for small codes, this could be useful because small codes could have gates that aren't going to be very big. And so, for example, the 4-qubit code, you can have a gate that just rotates by A1, A2, A1, A3 to get a logical gate on one of your logical qubits. Similarly, now, for anytime you see an X in CSS, you map it to a parity. And here, you preserve the unitarity of the stabilizers, and you can measure them in the same way you measure the X-type stabilizers in the CSS code. So the point here is that the Z-type stabilizers are mapped to these Lindbladian-type lowering operator monomials, and X-type stabilizers are mapped to unitary Gaussian rotations. The monomials can be used to protect your information using Lindbladians in a kind of like a continuous autonomous fashion. And the X-type parity syndrome things can be used to protect in a discretized or digital fashion in the same way you would do for your qubit error correction. Okay, so that's sort of a taste of these quantum spherical codes. I wanted to switch gears and briefly talk about another class of codes. Again, happy to field any questions from Hanho or others.
Yeah, I'm sorry if I'm monopolizing the conversation. This is mostly for individual qubits, or you can embed here multiple qubits and consider operations towards 2-qubit gates and things like that within this scheme, or
Yeah,
how do you think
yeah.
about it?
It's general. Every physical qubit is mapped to a CAD code. So any CSS code, QLDPC, what have you, can be mapped, can be concatenated with a CAD code. I mean, that's not what's new here. The new thing here is that, you know, there's this kind of Swiss Army knife of tricks that you can play that are based on the properties of the CSS code that are inherited in some way by the analog code.
And well, the complexity of the stabilizers remains the same because it's given by your qubit encoding. So it's at most you
Correct.
have four boson operators in this scheme. I understand.
Yes.
Great.
Yeah, that's what's interesting about it. The stabilizer part is interesting because if they're low weight, then you can have you can imagine doing low weight Lindblattans. It's not something that's completely crazy experimentally. The gates, the Z-type gates, are not so nice because if you say imagine a surface code, you know, there you can implement a Z-type Pauli by a transversal gate, but in this mapping you would have to implement it by something that where the modes are multiplied themselves, and that's not a very scalable thing.
That's it. Thank you.
Okay. So we've mentioned coherent states in the top right corner here as a sort of a basis to construct these quantum spherical codes. But the harmonic oscillator is very rich. There are very many other bases to construct codes out of for the oscillator. And I'm not going to go over all of them, but I'll just mention, I kind of want to mention in this slide that there are two kind of big families. There's the Cartesian way of interpreting an oscillator and the angular way. And the Cartesian way is just using lines. And the angular way is using circles and rays. So like a polar decomposition. And the circles are Fock states whose radius is just n. And there is a dual notion of states to the Fock states called the phase states, Peg-Barnett phase states. And these are rays in your phase space, and they're characterized by an angle. And anyway, each basis of these can be used to construct new codes or embed old codes. And each of the two pairs comes with its own framework for a noise, for quantifying noise, kind of a Cartesian framework in terms of displacement operators and an angular framework in terms of these operators I'll show you in a bit. So we're going to focus on the angular side of the story because I don't have enough time to cover the Cartesian part. And the angular description of this oscillator actually allows you to interpret the oscillator more or less as what's called a rotor. So let me review, first of all, what I am going to interpret the oscillator as before trying to do so. So the rotor, the planar rotor, the configuration space of that is just an angle. It's a particle in a circle. It's different than the oscillator because in the oscillator is a particle on a line. And you can get a rotor by identifying the line periodically. Because the position state space is compact, the momentum state space is discrete. And so while the momentum states of the oscillator, the Cartesian ones are again real, for the rotor, they're integers, okay? And it's kind of like, for me, the third big state space out there that people have been studying. It's not as well known because experimentally, it's actually been hard to realize. It is naturally present in Josephson junctions where phi is the superconducting phase difference and L is the Cooper pair difference. However, it's hard to simulate the actual bona fide circle geometry of the rotor. So often people approximate it with an oscillator. But things are changing and people are starting to kind of realize these types of angular state spaces. So we have a paper now where we worked out the Clifford group for the rotor in a bit more detail as has been done before. So anyway, back to the oscillator. The point is that this angular decomposition that I mentioned in the previous slide for the oscillator offers you a way to think of the oscillator as a rotor. okay? And I'll call it a number phase rotor. The mapping is not quite 100% because otherwise the two spaces will be the same. But there's many properties of or interpretations and geometry of the rotor that get preserved when using Fock states and phase states. So what's the difference? Well, you can think of phase states as the position states of your number phase, your fake rotor inside the oscillator, because both are parameterized by an angle. Now, phase states, the actual position states of a rotor are orthonormal, direct delta orthogonal, but the phase states of your oscillator are not quite orthogonal, and that presents some complications, but that's okay. The geometry still kind of makes sense. Dual to those phase states are states of momentum states of the rotor. Now, the momentum of the rotor is an integer. However, the best we have out at our disposal is the Fock states, which don't go below 0. Nevertheless, we can think this number, so this number phase rotor winds up being a planar rotor with its negative momentum cut off. And that's the reason the phase states aren't orthonormal, because there's no access to negative momentum. Now, you can imagine that the two systems are almost indistinguishable if you're high up enough in Fock state space, because there you don't see the bottom of the floor is cut off because you're kind of far away from it. As you get close to the bottom, you will see differences in the formulations of these two spaces, and this is something you have to take care of. But again, this offers a way to kind of understand the oscillator in a polar type or rotor geometry. And this type of position momentum, like rotational position momentum duality, gives you a set of operators that you can use to understand noise. And instead of linear shifts in position momentum, you have angular shifts in the angular position or angular momentum. So rotations, Fock space rotations, merely shift your position states, rotating your phase state around, so you can call them position shifts. On the other hand, you have these things called phase operators, which just shift you linearly without the square roots, without any square roots in the Fock space. And these are called Susskind-Glowrer phase operators or phasors. And they just, again, shift you up or down in Fock space by some number L, and L can be an integer. So these are mimicking shifts in the momentum of your planar rotor. They form a complete basis, and in principle, any physical operator can be expanded in terms of these position and momentum shifts, just like in terms of displacements. And moreover, any code that you can think of for rotors, well, that you can imagine codes for rotors, it may be possible to map them into the oscillator using this number phase interpretation. So one code that one can map into the oscillator was introduced in this paper by Josh Combs and Ben Barajol and Arne Grimsmo, is the rotor GKP code. So a GKP code I mentioned is a lattice, or you can think of the states as combs on a line. You can identify the line, and you can now have your combs lie on a circle, like in the upper right. And the protection against errors works in the same way. It's basically kind of like the same way as a cat code, right? You have points on a circle and some polytope. This is done for the rotor, though. If you now take that planar rotor and just cut off the negative momentum states, you get a number phase rotor inside your oscillator, and you get these number phase codes. So if you think of these, if you now use the phase states of the oscillator as opposed to the position states of the rotor to construct these codes for the black and white balls, you get what are called number phase codes. And these are protected against sufficiently small rotations, rotations in this case by like 2 pi over 6 or something like that. If you write these states in Fock space, in angular momentum space, you will see that they're spaced apart in Fock space as well, and so they can protect against losses and gains. And this kind of mapping also allows you to have more or less kind of stabilizers for your codes. So unlike the cat codes, where the phase like operators are lowering operators, here for phase states, the phase flip noise and the Z-type stabilizers are quantified by these phasers, or these Susskind-Glore phase operators. And those phase operators are more well-behaved than the lowering operator in that they're one-sided unitary. So like U dagger U is identity, but U dagger is not. And so this allows you to have at least some semblance of a stabilizer set. It's no longer a group because these things are only one-sided unitary, but the fact that they're one-sided unitary actually allows you to write them as a semigroup or a monoid, meaning that there's no inverses, but you could still kind of multiply them together. And so you have this, basically what was the stabilizer group of the rotor GKP code in the planar rotor space becomes this stabilizer semigroup, monoid, technically, in the oscillator picture. Likewise, you can play this game with another set of multi-rotor codes that were formulated by Christoph Vio and company, and Barbara Terhal and others for rotors. And those are called homological rotor codes. So this is from, this is from Christoph's paper. This construction was motivated by these homological CSS codes, where there's these deep connections to homology between the two matrices you use to define the code, and these things called chain complexes, which are just things which have boundary maps that such that boundaries don't have boundaries. And this boundaries don't have boundaries statement is equivalent to equation 1 in this slide, if you think of each matrix as a boundary map. And this stabilizer group is defined using these two integer matrices for the homological rotor code. And this is inside the rotor subspace only. However, using this number phase kind of interpretation of the oscillator and another trick where we rotate by flipping the momentum so that the codes lie in the right orthant, in the all positive angular momentum state space, we can map these into the oscillator using the number phase interpretation. So again, each oscillator can be thought of as a rotor with no negative momentum. And so if you have n rotors, you have a rotor code on n bona fide rotors, you have to make sure that the code remains when you cut off the momentum of all the rotors. And this is something that you can always do by flipping around the momenta of the rotors, of the individual rotors, in a way that now the code words have substantial support on the all positive momentum state space. So once you do that to your rotor code, you can then safely cut off all the negative momenta, and you have a number phase homological code. What's interesting about this is because
Victor, sorry to interrupt you, but we are already over time, so in 5 minutes or so you should be ending.
Yeah. Let me mention one slide then. So if you go back to the spherical codes, so let's see, syndromes for these continuous variable codes have to be what's called modular. You can't measure the position because you collapse everything. You can't measure the momentum and to get just one value, because everything, all the white and black balls will collapse. You have to measure the momentum modulo something for lattice codes. Similar for spheres, you have to measure positions modulo some tiling. Okay, and if you think about circles, the way to do that is using what are called using this phase state measurement that some of you are familiar with. And for quantum spherical codes, we generalize this phase state measurement using hyperspherical or spherical states in n-mode space that are rays in n dimensions now, as opposed to just a circle. So this is something I wanted to flash. We think this is also an optimal way to measure a point on the sphere, but we haven't proven it. We did prove the following equations, that these are generalizing the phase states in this way. So anyway, the rest was just review. So many things can fit into CV systems. I didn't talk about these Cartesian things, these lattices, but I just want to flash them here. There's also angular things that I did discuss. You can put circles in phase space. You can generalize circles in two ways, using spheres or using donuts. And I talked about two codes that do that. There's a third way I didn't discuss using Fock states. Some of these things are groups. So lattices form groups, tori are groups, circles are groups, hyperplanes are groups. There's a group theory way of understanding codes that are groups. But some are not. And so the spherical codes offer a way to kind of extend error correction, quantum error correction to non-group spaces. And I think there's more work to be done there. So with that, I want to highlight my students who did the work for this homological rotor mapping and some of these Clifford operations, as well as these quantum spherical codes. I'm happy to say we're conditional on some formatting issues. We're accepted to Nature Physics for the second paper. And with that, I want to thank you for your attention.
Okay, thank you very much, Victor. Sorry for the interruption before. I just was because people are already leaving, and well,
I remembered that it was supposed to be 40 minutes when you told me now. So sorry about that.
Sorry, but no worries in any ways. Okay, so thank you very much. So if anybody has some questions, now it's the time to ask.
I have maybe a qualitative question. So the nice thing about CAD codes is that they simply reflect the fact that some experiments are biased. The error is biased towards certain events that are more probable than others. These spherical codes, or the codes that you presented with CS and coherent states, do they capture those advantages in some way, or do they simply extend the theory of error correction to continuous variables?
I think they do, because the reason you can get a noise bias protection is because there's a gate that flips your cat code states that keeps their distance while keeping their distance. So any kind of and that those gates also exist for spherical codes, like all those icosahedral gates. They just isometrically rotate the polytopes into each other while maintaining their separation. And so if you're able to do those experimentally in some conditional way, conditional on some other qubit, then you should also have, we didn't work it out in detail, but we would conjecture you should also have a bias preserving kind of situation.
Nice, thank you.
Okay, anyone else wishes to ask something to Victor?
We don't have to record the questions. Maybe people will be more brave.
Yeah, okay.
We can cut them.
We can stop, yeah.
Yeah, maybe just once to pick